That's 215. Certain problem is about Raoult's law, right? Yeah. It's about dissolving a non-volatile substance in water, volatile substance, right? And nobody showed up to videotape this section for the ones that are going to make it. No one from your class. But there was one from a previous quarter, thanks to Will. He's videotaping right now. You give him a clap. Thank you. So if you want to watch it again, it is due to Will's selfless action. You will be able to watch it if you want, and people that do not come. It's because of his selfless action. Like he did today, you do it tomorrow for others. Will you? Then you will have a clear mind. Then you can be a top student like he is too. He was the top in his class. Why? Because he's doing selfless actions. Yes, most of the time people, that they do really well is because they think about other people too. You think it's not true? How about if you try it? See if it will work for you. Try it. Just try it. Just try it a little bit. See what will happen. Okay? So here is a problem that is related to Raoult's law, right? So what do we have? Basically, we have water. You put sugar into it. We consider that the ingredients are just nothing. We assume it's not much. So we want to find out the new vapor pressure of water. That means now as in the form of solution after you dissolve so much sugar for so much water, right? So it's really basically applying a simple application of Raoult's law, right? You realize that, okay? So everything is done at the same temperature. So Raoult's law says that the pressure of the solution is going to be equal to the mole fraction of the solvent times the vapor pressure of water, the solvent, when it's pure, nothing in it. So what we really need is, we know this is giving us that, right? It tells us that the pure water. So we know this. The only thing we need to find out is really the mole fraction. Okay? And so by definition, mole fraction of water is equal to what? Moles of water divided by moles of water plus moles of sugar. That's the definition. So moles of water will be equal to the mass divided by the molar mass of water. So that will be 230 grams divided by 18.02 grams per mole. That will give you, well, 76 moles of water. Okay, and the number of moles of sugar is going to be equal to 5.0 grams divided by the molar mass of sugar. It gives it to you because there are many types of sugars, right? This is one kind of sugar. There are a lot of sugars with different molar masses. Moles of sugar, and so the mole fraction of water is going to be 0.998. So from that, we'll have T solution. From here then, we'll have T solution is equal to the mole fraction times 400. This is unitless number, no units. the whole fraction, 406 millimeters mercury. So that will give you 400 millimeters mercury, right? And as you can see, it's smaller than when it's pure. When it's pure, it's 400.6. You put sugar, the vapor pressure should go down. So now it's less. 400 is less than 400.6, isn't it? Right? So you can check if you've done any mistakes that way. You always think. You just don't do the number, okay, you choose the correct number, right? You always think. There's always requirements. Vapor pressure lawyer, that number has to be less than 400.6. Okay, let's, I like to put this problem here, as you can see from different practice exams. I change every time the different examples. So here is to really understand the definition of work, energy in the form of work, and work can be different types. Pressure, volume work, radiation work, electrical work, blah, 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 blah. There's a lot of types of work. Energy transfer from one system to the other, or in general from the system to surroundings and vice versa, in different types of work. And then, besides that, we have energy transfer as heat. And energy transfer as heat is happening only if you have a difference of temperature, right? But in contact, continuous contact, or momentarily, like particles colliding to a surface. These things are not clear in the books at all. So make it clear tonight. Difference of temperature in contact, or even temporarily by a continuous bumping of molecules to the surface. That's heat transfer. Anything else, energy transfer is, we say, in the form of work, and it could be different types, as I mentioned before, right? So if you have that in mind, then this problem very clearly identifies for you both systems. It tells you system A is this, system B is this. So by knowing what the two systems are, then you can choose if the energy transfer between them is in the form of work or heat. So you will see the same problem in your exam, but it's not going to be the same examples. They're going to be different examples. They might be all of them work, they might be all of them heat, or they may be mixed up. So make sure you understand these definitions, and then that's a piece of cake problem, right? Okay, so that's kind of an example there. And then we have number 3. So number 3, you have water as the one system, you count. The water is the system A, and system B is the microwave oven. It's a total thing, just a total thing, microwave oven. So in that case, what is it? Work or heat? Huh? Heat? How many heat? Say heat. How many? No, it's work. Microwave. What do you mean? Work in the form of radiation. Is the microwave work? No, it's not. Touch it before you press the button. There's nothing there. There's no higher temperature. The water, you assume water and microwave in the same temperature. So you pick up the cup out, and it's really hot. You go and put your hand in the microwave after it's done, it's real hot. It's not going to be hot. So what happens? Okay, so it's in the form of radiation, in the form of work. Radiation is a form of work, by definition. Okay, so it's work. How about 3? I mean 4. How about 4? So water is the system, system A, electrical outlet is B. What's energy transfer from one to the other? What is it? Q or W? How many people say Q? How many people say W? Okay, so most people got it right. Yes, to be? work. How about 5? Two. W. Hey, you guys don't know, huh? Come on, this is easier. How many people say it's true? How many people say it's work? Oh, okay. You got it. How about 6? You see, pressure, volume, work, right? It's no friction. It's a different thing. Friction is different thing, right? Some comes from friction, but most of it comes because of compression, which is hard to explain, but not that bad. We're not going to go into one. How about 7? 6 is W. How about 7? You are divided, huh? You are divided. No. 7 is... facing the fire. It doesn't say they're close to the fire. Facing. They're just facing. If you don't face the fire, then you go to the next one. You're not facing the fire now. You're just in a warm room. You don't have to face the fire. You can be all the way down there. That's not radiation now. It's because of the air molecules. They go fast. They collide with your body. They give you motion, thermal energy. That's in contact, even momentarily, right? In contact. And that's energy in the form of heat, because the air is higher temperature now than your body, above 37, and you have transfer from the air molecules into your skin, right? So that's going to be Q. How about 9? How about 9? What is 9? 9 is work. Friction, right? Because of friction. How about 10? Okay, that's pretty easy.